Okay, so today we have with us a young speaker who is about to finish his master's, Aditya from IIT Madras. Okay, please, Aditya, you can start.
Yeah, thank you, Roger, for thank you, Matthew, also for inviting this for this talk. Regarding me, I am doing my master at IIT Madras under the guidance of Nishad-Kothari. So today I am going to present our work which we had done over last couple of years on the planar cycle extendable graph and related graph classes. Don't worry about the terms. I will introduce each and every term in this talk. Before starting, I wanted to dedicate this talk to Professor Ajit Diwan, who has recently passed away, and he has a very good contribution in my whole research which I had been done. So yes, and this photo from which we visited Ajit Diwan in last year, and red wearing a red T-shirt is me. So yeah, so let start the talk. Yeah. So this is a graph. We call this graph as a H8. Let's start with the definition of perfect matching. A perfect matching is a set of blue edges such that if you consider any vertex, there is exactly one blue edge incident on it. So this is a formal definition of a perfect matching. And a non-trivial graph, we said, is a matching cover if the graph is a connected and each edge belongs to the some perfect matching. So, in the study of perfect matching, one may restrict their attention to the matching code graph, and there has been a lot of literature in the matching code graph. You can refer a Loas Plummer book of a matching theory, where they say this graph as a one extendable graph, where each edge of a graph we can extend to the perfect matching. What mean of extends to the perfect matching is, consider an edge. Now you can extend that edge, means you can add some edges in the set of this one edge and finish the perfect matching of the graph. Now we can generalize this definition by k extendable graph, which a matching in a match like which is a matching colored graph in which each matching of cardinality k extends to the perfect matching. So yeah, there is a lot of literature regarding the one extendable graph and k extendable graph. Especially Plummer has a work in a k extendable graph a lot.
One
And
extendable is one extendable is same as matching covered, is it?
exactly. So this is a definition which in the literature people use quite a lot. And the one extend here the one extendable k extendable I introduced because this is one of the motivation we gave a cycle extendable name, and we'll see the why it is in the next slide. So if this is a clear, we can go and define what is cycle extendable graph. Okay, let's go and define cycle extendable. For a matching curve graph G, we say graph is cycle extendable if for each even cycle, each perfect matching of C, like even cycle has a two perfect matching for a just even cycle. Now we can extend a perfect matching of C to the perfect matching of the graph. So if we can do for this for each even cycle, we call this graph as a cycle extendable graph. Equivalently, we can say the graph after removing the vertices of C has a perfect matching. And equivalently, we can say C is a symmetric difference of a two perfect matching. And the fourth equivalent requires a decomposition theory. Beforehand, let's see this graph is cycle extendable or not by just the definition. So if it is no, we have to give me a one cycle such that if we remove the vertices of that cycle, the remaining graph does not have a perfect matching. So is this graph is cycle extendable? No, if you see this cycle carefully, this six cycle with the dashed. So if you remove the vertices of this cycle, we have remaining with the two isolated vertex after deleting the vertices of C. So this graph is not cycle extendable. Okay. Now what about this graph? Is this graph is cycle extendable? since I give you one example of non-cycle extendable graph, this graph should be cycle extendable. Yes, this graph is indeed cycle extendable. One can check extensively with the each even cycle. If you remove the vertices of each even cycle, the remaining graph has a perfect matching. So this one example is not a cycle extendable. This example is cycle. Before going, I will introduce the fourth equivalent. We need one more definition. We say a subgraph H of a graph G is a conformal if the graph after deleting the vertices of H has a perfect matching. Now, by the just definition of conformal subgraph, we can change our first definition of cycle extendable by saying that each even cycle in cycle extendable graph will be conformal. Right. So we see the equivalent definition. Let's try to define our problem statement. What we want to, so our main goal is to characterize cycle extendable graphs. And if we see this problem in terms of decision problem, that given a matching code graph G, decide whether G is cycle extendable or not. Does it belonging to co-NP? That means it's easy to convince your friend that a given graph is not cycle extendable. So yes, it is belonging to co-NP. So we will just give a one cycle such that it is not conformal. That means if you delete the vertices of that cycle, the remaining graph does not have a perfect matching. So it is belonging to co-NP. But what it is belonging to NP by just looking the definition of cycle extendable graph. So it seems not be, because we have to check for all cycles and there will be exponentially mini cycle in the graph. So we have to check it for all. So it's not known that it's belonging to NP or not. So is it clear what the problem statement we are looking at? Okay. So let's see our fourth equivalent definition, which requires ear decomposition theory. It is a similar ear decomposition theory for two connected graphs, but we will see for the matching chord graphs. Okay. So what is ear first? Adding an ear to the graph is, consider two vertices of a graph UV. Add an odd path to it such that whose endpoints are U and V, otherwise it is disjoint from the graph H. So it is calling that adding a single ear to the graph. And what is adding a double ear? Consider four distinct vertices WX, UV, and add two single ear simultaneously. So it is called as adding a single ear and adding a double ear to the graph. So let's see an example of adding an ear. So consider the graph G, which is H8, which we are looking from slide number 1. Observe that this is a cycle of a G, which is a conformal. What is conformal means, if you delete the vertices of this cycle in the graph G, the remaining graph has a perfect matching. So this is a conformal cycle Z0. Now let's add a single ear to a cycle. So we add a single ear to the graph. Observe that G1 is also a matching chord graph. That means each edge of G1 belongs to the some perfect matching. And now we want to construct a graph G which remains with the two edges E and F. Now if you add either of one edge, either of the edge, the remaining graph cannot be matching chord. Means if you just add E to the graph, then you can observe that E cannot belong into any perfect matching. So for getting matching chord graph from G1, we have to add E and F simultaneously. So now our main goal, now we want to construct a graph which all this intermediate graph is also matching chord. Whatever the sequence we saw is called as a ear decomposition. What is the ear decomposition of a matching chord graph? A sequence of conformal matching chord subgraph G0 to GR such that G0 is a conformal cycle, Gi plus 1 is obtained from Gi by adding a single ear or a double ear. And obviously our graph GR
So
should
the
be graph
years
G.
have, the years have even number of new vertices, is it?
Exactly. Odd path, I said. Odd means number of edges in that path should be odd.
Okay. So you are saying each GI should be conformal. Is it the entire GI should be conformal?
Exactly. Entire GI should be conformal in G.
Conformal in G, correct? Yeah. When you remove
Exactly.
GI, the remaining thing should be have a
Have
perfect
a
match.
perfect match. Exactly. So now the question arises here that each matching code graph has a year decomposition sequence. So when we saw a graph H8 is a matching code and we have a year decomposition sequence. And now the question is every matching code graph has such kind of year decomposition sequence? And the answer given by Loas Plummer in 1987 that yes, each conformal cycle of a matching code graph G extend to an year decomposition of G. That means we can get that graph G by starting at a conformal cycle, either adding a single year or a double year, and we can construct the graph after doing this sequence of the operation. And that is our force equivalent definition that since our all event cycles should be conformal, that in the cycle extendable graph, so that all event cycle can be extended to the year decomposition of the G. So is it clear that four equivalent definition and kind of motivation also like why we want to talk about cycle extendable? Okay. So going further, our problem statement which we are looking at that we want to characterize all cycle extendable graph. So what we already known. So bipartite planar cycle extendable graph is already known characterization from 2004 and claw-free planar cycle extendable graph from 2020 and claw-free cycle extendable graph from 2022. And one of our key contribution to characterization of planar cycle extendable graph, all planar cycle extendable graph in terms of K2 and 4 infinite family. Our result is a generalization of our first two results. And our graph H8 will belong to one of our 4 infinite family. And next we'll see a brief overview of our approach. Okay. So now our main goal to characterize all planar cycle extendable graph. So we are currently looking our planar cycle extendable graph in a matching code graph, which is a very big family. For an example, you take two connected three regular graphs, one can easily prove that this all are matching covered. So this is very big class of graph and we are finding all planar cycle extendable graphs. So for that, now we have to reduce our search space to find this class of graphs, right? So let's start to do that. Our next step is to reducing the search space. So remember, we are allowing a multiple edge in the matching paragraph. So let's see first parallel reduction. So let E and E dash are the parallel edges. Now remove the one parallel edge. So we got a graph H. One can say that graph G with the parallel edge E and E dash is a cycle extendable if and only if graph H is a cycle extendable. So we did a parallel reduction. We remove multiple edge and one can say graph G is cycle extendable if and only graph H is cycle extendable. Similarly, let's do a series reduction. Consider a path of length 3 whose internal vertices W and X are degree 2. Now we can replace this path of length 3 with the one edge. Same graph G is cycle extendable if and only graph H is cycle extendable. And we say a graph is an irreducible graph. That means either of the reduction is not possible. That means a graph is simple and its degree to vertices comprise a stable set. And the following proposition we just now proved, let G be a matching chord graph, and H be a irreducible graph by doing a repeatedly application of series and parallel reduction such that a graph G is cycle extendable if and only graph H is cycle extendable. Now it suffices to characterize all irreducible planar cycle extendable graph. Okay. So now further also we will reduce our search space, but before that we need some of the matching theoretic theory. First I will introduce that theory and then we will go further. So let's see the theory. The theory is called as a tight cut decomposition theory. So beforehand, what is a cut? For a matching cut graph, partition the vertices x and x bar, and the set of cut is a set of all edges whose one end in x and another end in x bar. So this is a cut. So in this example, we'll denote as a parcel of x. So if you consider this example, blue line indicate the cut of the graph, right? And operation cut contraction, that means shrink all the vertices of x into the one vertex, and similarly shrink all the vertices of x bar into the one vertex. So this is an example of the cut contraction by the given cut. So if you do a cut contraction in the right hand side the graph, you will get one as a K4 and another we will replace one vertex with a this is another graph. So this is a cut contraction operation. So this is a cut and the cut contraction operation. Let's define a tight cut. What is a tight cut? Tight cut is a cut such that for every perfect matching M, it will intersect the set of edges of cut, it will intersect with the exactly 1. And the size of x and x bar will at least 3. So this is a cut. And by the definition of tight cut, one can easily see that both tight cut contraction are also matching cover. Especially, it will be smaller matching cover graphs. Right. So let's see. So consequently, this is also if you consider this graph, this is a matching cut graph, and the blue is a tight cut for the graph. We did we did a cut contraction, and we get a two smaller matching cut graph. Now we ask the same question in the smaller matching cut graph: is there any tight cut in the two smaller matching cut graph? If there is, then we can decompose to it to further smaller matching cut graph. And when we can repeat this procedure until then we will get a graph which are free from the tight cuts. So if you consider the graph which will get K33 and two K2s, these three graphs are free from tight cuts. And whatever the procedure we did just now, it's called as a tight cut decomposition procedure.
Aditya, what was your definition of tight cut?
Yes.
Exactly one edge intersects any perfect matching, is it?
Exactly.
Okay. And here I did not understand the picture. You contracted those three vertices into one, is it? The one
Exactly, yes.
below the
Yes,
blue
yes.
arc, you contracted all three of them. Which is that vertex on the left side?
Here, this one. Is it?
Okay, what
Let
is it?
me.
Why do you have a K4 on its side?
So we can contract other side as well, right? So there will be x and x bar. So we will contract the other side. So
other side will be
other side will be all the these three vertices. This let me show you with my mouse. Is my cursor visible?
Cursor is visible, yes.
Okay, so if you contract all the vertices here,
Right.
you will get K4. And if you contract this triangle, you will get this graph.
I mean, you contract, you get just one vertex, right? Okay.
Sorry, shrink. We will do a shrink of the all the vertices.
Okay.
So this cut will partition the vertices in two sets. Let's say we call all these vertices as x, and we will call this triangle as a x bar.
Okay.
if you shrink all these vertices in X into the one vertex, we will get K4.
Correct.
Exactly. And we will contract this we will shrink these three vertices into one vertex, we will get this graph.
Okay, I got it. Yeah, yeah.
Yeah, this is a cut contraction, tight cut contraction as well.
Okay, okay. And those two graphs are not connected. They are in the picture. They
Yeah,
are.
yeah, actually, yes. It's not
Okay.
connected.
Okay.
So now here we did the same. Now we ask the same question in the two smaller matching code graphs, that is there any tight cut? And if it is, then we will do a further tight cut contraction and we will get these three graphs. One is a K33 and two copies of K4. And we can repeat this procedure until we will get a graph which are free from tight cuts. And this procedure called as a tight cut decomposition procedure. Yeah, so we did a tight cut decomposition procedure for this graph and we got three graph with three matching code graph which are free from the tight cuts. One is a K33 and two copies of K4. And we will say a matching code graph is a free from tight cut. It is a brace if it is a bipartite, otherwise it is a brick. So yeah, now the question is now I give one matching code graph to person A and I give same matching code graph to person B. Now person A and person B did the tight cut decomposition procedure independently. Means person A did a tight cut decomposition procedure and get some list of brick and braces, the matching code graph which is free from tight cuts. Now person B did tight cut decomposition procedure and get a list of brick and braces. And the question is, since I give a same matching code graph to person A and person B, is this list of brick and braces also have some relationship? And the question asked by Loas and uh, give the answer in 1987 that any two application of tight cut decomposition procedure yield the same list of brick and braces up to multiplicity of edges. What it means? Person A will get some list of brick and braces. You take underline simple graph. Person B will get some list of brick and braces. You will take underline simple graph. The both lists are same. Yeah. So this is one of the groundbreaking result in matching theory. There is a lot of consequences of this theorem, and some of them we will see in the next slide. Is there any doubt till now? So this is the remember this is a theory which I am introducing to reducing the search space for our planar cycle extendable graph. Okay, so let's see some of the consequences of this unique tight cut decomposition theorem. So it will show that the following are the invariant. So number of bricks of a matching code graph G, number of bricks we will get in the tight cut decomposition procedure is an invariant. Similarly, number of braces we will get in the tight cut decomposition procedure is also invariant. We'll say B of G is a number of brick and B dash of G is a number of braces. And one can easily see that for a bipartite graph, we'll get number of bricks in the tight cut decomposition procedure is 0 because brick is a non-bipartite graph. If we get at least one brick in the tight cut decomposition of a bipartite graph, then whole graph cannot be bipartite. So yeah, now the question is what? So yeah, this is one example of a bipartite graph with the where the blue line is a tight cut. Now the question is what about this class of graph where we will get number of braces in tight cut decomposition procedure will be 0. It's also that it's turned around that it's also very well-known graph class called as a bicritical graphs. A graph we say it is a bicritical if it is have at least 4 vertices and for any two pair of every pair u and v, the graph after removing u and v has a perfect matching. So it's called as a bicritical graph. And this is an example of bicritical graph where the blue line is indicating a tight cut for the graph. You can see, you consider any two vertices u and v distinct. If you delete it, the remaining graph has a perfect match. And a graph is a bicritical if and only if the number of braces you will get in a tight cut decomposition procedure is 0. So don't worry about too much terminology here. We just need B of G, which is number of bricks of a matching code graph for this talk. I introduce B dash of G to this kind of one of the invariant in a tight cut decomposition theorem by Loas. So we need B of G for the remaining talk. What is B of G? For the just reminder, the number of bricks, number of non-bipartite graph which are free from the tight cut in the tight cut decomposition procedure. So let's see. So is also there is another equivalent definition for a brick by Elman, Loas and Pulley-Blank. A graph G is a brick if and only it is 3 connected and bicritical. And what is a near brick? A near brick is a matching code graph where B of G is exactly 1. What it means that you will do a tight cut decomposition of a near brick, you will get exactly 1 brick in the list of brick and braces. And this is the example of a brick, first example, which is indeed a Peterson graph. This is a brick. This is an example of a near brick where B of G, you will get, if you do a tight cut decomposition, you will get 1 K33 and 1 K4. And this is not a near brick. That means if you do a tight cut decomposition procedure, you will get 2 K4. That B of G is equal to T2. That means it is not a near brick. And first to graph is a near brick. That means a brick is also near brick. Okay. So now our next goal to that there's a matching theoretic implication of cycle extendability. Means we will going to reduce the search space further. So let's see. There is a theorem by Carvalho and Little from 2008. What it says for a matching curve graph G, if B of G is at least 2, then there exists an even cycle that is not conformal. That means if we got a brick in the tight cut decomposition procedure is at least 2, then there exists a cycle in the graph such that if you delete there exists an even cycle in the graph, that means if you delete the vertices of that even cycle, the remaining graph does not have a perfect matching. And the following is an immediate corollary that every cycle extendable graph is either bipartite or otherwise a near brick. So now we have to only characterize bipartite and near brick cycle extendable graphs from the above theorem. Yeah. So now let's we will find some of the facts useful in the for the further talk. That brick and braces are 3 connected. We saw bricks are 3 connected by Edmund Lower's Pulley-Blank theorem. Now braces are also 3 connected except K2 star and C4 star. What is K2 star? K2 with the multiple edges and C4 star means C4 with the multiple edges. And we can see for a cycle extendable graph and parcel X is a tight cut, the both tight cut contraction is also a cycle extendable. And consequently we can say that each brick and braces are also cycle extendable. And only planar cycle extendable braces are K2 star and C4 star. So one observe that till second point, whatever the result we saw, it is true for the general graph. We didn't impose any planarity condition till now. Only third point, which is talking about planar cycle extendable graph. So whatever the result we saw for the second point is true for the general cycle extendable graphs. Now our goal is to characterize a planar cycle extendable graphs. So now we will impose a planarity condition whenever it is needed. Okay, so let's go. So in the planarity, we will prove that for a minimum degree at least 3, it is a brick. So what our theorem is, for a simple planar cycle extendable graph with the minimum degree 3, then the graph is a brick. Yeah. So let's prove this theorem. So G, we prove this, a G cannot be a bipartite graph using a result of Chartrand, Kaugar and Lick. What it says that if graph is a bipartite, then it will in the minimum degree 3 case, there will be a even cycle which is not conformal. So yeah, so now onwards G is a non-bipartite graph. So G will be a near brick from the theorem of Carvalho and Little. What Carvalho and Little theorem saying that every cycle extendable graph is either bipartite or a near brick. So now we say G will be a non-bipartite graph. So G will be now onwards G is a near brick. Suppose to the contrary, G is a not a brick. That means there exists tight cut. There exists a tight cut in the G. So let's if we denote as a parcel of X. Now consider a both cut contraction for the given tight cut. Now what we can say, a number of bricks of G1, that B of G1 is 0 and B of G2 is 1. So suppose for the contrary, number of bricks in G1 we will get 1, number of bricks in G2 also we will get 1, which will contradict that G is a near brick. So either number of bricks in the G1 will be 0 and number of bricks in G2 will be a 0. But yeah, so without loss of generality, we get number of bricks in the G1 will be 0. Now suppose that G1 is not a brace. That means there exists a tight cut in a G1. So, and one can easily observe that the same set of vertices, same set of edges will form a tight cut in the G as well. So now we can choose a tight cut in G such that if you shrink all the vertices of X bar will be a brace. And we saw in the previous slide that all brick and braces of the cycle extendable graph, it should be also cycle extendable, and the only planar braces are K2 star and C4 star. So now G1 will be a K4 star. It cannot be K2 star because of the tight cut definition. That means at least X bar has to at least three vertices. So it will be a C4 star. And if you see in the main graph, the figure will look like this in the middle, which I show.
So,
And
Aditya, can you
yes,
hear me? So for every tight cut in a matching covered graph, I suppose both sides of the cut they induce connected graph, right?
yes,
So
yes,
that is why after contraction also this is planar. I mean after
exactly,
identifying. Okay.
exactly, yes, yeah. So what Matthew
Okay,
is
thank you.
saying, yeah. So yeah, both once we do a contraction, the resultant graph also will be planar. So the only planar braces are K2 star and C4 star. We cannot get a K2 star in the contraction because at least we need at least 3 vertices. So we will get a C4 star. And we see a same figure in the result in the graph G. We have a vertex of degree 2 because we start or let's say is a V, and which is a contradiction that minimum degree of a G is at least 3. And we prove that graph will be a brick. So now we'll show first a brick characterization and then we will show the general characterization for all planar cycle extendable. Okay, So for the characterizing a brick, we need two more result. Let's see, our first result is a planar cycle extendable graph, which implies K23 free. What is K23? What is K23 free? I will define it. Beforehand, what is a by subdividing an edge UV? By subdividing an edge UV means we can replace edge UV with a path of length 3. This is just a reverse operation of a series reduction. And what is a by subdivision of a graph? By subdivision of graph is consider any subset of our edges and by subdivide it at any time, any time you want. Yeah, we can recursively by subdivide each edge. And what is K23 free means a matching curve graph is a K23 free if G does not has a subgraph that is by subdivision of K23. Otherwise, we will call this graph as a K23 based. So yeah, and Gu and Zhang in 2004 proved that for a planar matching code graph, if G is cycle extendable, then G is K23 free. Now let's try to see this lemma. We'll prove the contrapositive of this lemma. Suppose let G be a planar matching code graph. Suppose G is K23 based. Since it's a planar, consider the planar embedding. Since there exists a by subdivision of K23, which is K23 based, so it will look like, so in the graph, the by subdivision of K23 will look like this. It will partition the remaining vertices in F1, F2 and F3. So we are considering a planar embedding of graph G, and since graph is K23 based, the K2 by subdivision of K23, it will look like this, and it will partition the other vertices which is not present in graph by subdivision of K23 in 3 parts. One is F3, F2 and F1. Since the number of vertices in the by subdivision of K23 is odd, the either F1, F2 and F3 has an odd number of vertices. So without loss of generality, we can say F3 has an odd number of vertices, and one can easily observe that outer cycle of by subdivision of K23 is not extendable, means is not conformal, because the F3 has an odd number of vertices. There cannot, so odd number of vertices cannot be having a perfect matching inside it. So which shows our K23 free lemma that for a planar matching code graph, if G is cycle extendable, it should be K23 free. Okay, so let's see our second thing. For a 3 connected graph, a mixed bicycle will implies a K23 based. Means if, let's see first what mixed bicycle is. A mixed bicycle is a pair of vertex disjoint simple cycle of different parity. Simple cycle here means we are not allowing C2, K2 with 2 parallel edges. So yeah, and what our result is, for a 3 connected matching code graph, matching code here is not required. It is true for all 3 connected graph. If G has a mixed bicycle, then G is K23 based. That means if G has a mixed bicycle, then G has a by subdivision of K23. I won't prove the formally here. I will give you a hint. Since graph is a 3 connected, by Menger's theorem, there exists a 3 vertex disjoint path. Let's say P1, P2, and P3, whose one end in QO and another end in QE. And from here, now just looking at 2 cycle of different parities and looking at 3 vertex disjoint path, you can construct a by subdivision of K23. By subdivision of K23 is nothing but 3 vertex disjoint even path, internally vertex disjoint even path, whose so now you just have to find 3 internally disjoint even path using this mixed bicycle and 3 vertex disjoint path P1, P2 and P3. So yeah, from here now we can complete proof easily by just looking at 3 paths and mixed bicycle. Does anyone having question in this K23 free lemma which we saw earlier in mixed bicycle lemma? Okay. If not, let's try to put everything together and try to see a characterization of our brick. What it say? Let G be a simple planar brick. G is cycle extendable. Then G is either a wheel or a prism. So what is a wheel? Consider an odd cycle, introduce the one vertex and make it universal. So this is our definition of wheel. Yeah, wheel has a general definition, but we will restrict with this definition because other wheels are not matching cover. So this is a wheel which we define. And what is a prism? Consider a two vertex disjoint odd cycle of same parity and join it, connecting both of it with the perfect matching. So this is a prism. So both are the infinite family. So remember, we are proving that G is a simple planar brick and G is a cycle extendable if and only if G is either a wheel or a prism. By just looking at the definition of wheel and prism, one can easily convince that both are cycle extendable. Now our main goal to prove a forward direction that for each simple planar brick is cycle extendable, either a wheel or a prism. We will prove a contrapositive of it. Suppose G is neither a wheel nor a prism. Then we proved that G has a mixed bicycle using a Norrin-Thomas brick generation theorem from 2007. This is one of the tool which we use frequently in our work. So by Norrin-Thomas brick generation theorem, we proved that if it is neither a wheel or nor a prism, then G has a mixed bicycle. By our mixed bicycle lemma, and since bricks are 3 connected, we can prove that G is K23 based. That means G has a bisubdivision of K23. And which implies by our K23 free lemma, G is not cycle extendable. Okay, so here we characterize all simple planar bricks. If it is cycle extendable, if and only if it's either a wheel or a prism. Now let's see our whole characterization of planar cycle extendable graph. Let G be a sorry. Sorry. So yeah, let G be a irreducible planar matching chord graph. What is irreducible? It is simple and its degree 2 vertices forms a stable set. So let G be a irreducible planar matching chord graph. G is cycle extendable if and only G is either a K2 and belong to our 4 infinite family G0, G1, G2 and G3. First I will define 4 infinite family and then we will see a proof sketch of main theorem as well. Okay, let's go and define our 4 infinite family. For that I require a half biwheel family which is a bipartite planar cycle extendable graph. What is half biwheel? Consider an even path UV, introduce a vertex H and make it join with the all black vertices of even path. We'll say UV is a corner of half biwheel and H is a hub of the half biwheel. So this is a smaller member of half biwheel. And this is a smallest member of the half biwheel where we consider a zero length path, introduce a vertex H and make it join with the black vertex. So this is a half biwheel family. Now using half biwheel family, I will introduce all our 4 infinite family. So now let's define our Z0. We called as a generalized prism. We'll clear it why we call this generalized prism. Consider a K half biwheel where K is odd and at least 3. Now adjust half biwheel, either hub is upward facing or hub is a downward facing. and then add the following edges in the particular manner. Now, if you take each half biwheel is a K2, then the resultant graph is a prism. The K2 is our smallest member of half biwheel. So yeah, that's why we call is a generalized prism. This is a kind of generalization of a prism. Same as G1, where G1 is a generalized wheel. Take K half biwheel, K is odd and K is at least 3. Identify all of its hub into the one vertex and add the following obvious edges to make it like a generalized wheel. Same, if you consider all half biwheel is a K2, then the resultant graph is a wheel. Yeah. Now, double half biwheel. As name suggests, take two half biwheel, put one in a downward hub facing and one is a upward hub facing, and add four following edges. We won't allow either of the half biwheel as a K2. That means we will take at least C4, which is our second smallest member, either of both of the half biwheel. Means like we want all four family as a disjoint. If we take either of it K2, then it will intersect with the either generalized wheel or generalized prism. So this is the definition of double half biwheel. And last family is hexagon half biwheel. As name suggests, consider one hexagon, a 6 cycle, and one half biwheel, and add four following edges. And now if you take half biwheel as a K2, then the resultant graph is H8, which we are looking for the slide 1. And as I said, H8 is belonging to one of our four family. Yeah. So what the main theorem we are looking at, let G be an irreducible planar matching per graph. Let G is a cycle extendable if and only G is either K2 or belong to 4 infinite family. As usual, once we know the definition of all four family, it's easy to prove that all members are cycle extendable. Our main work is to prove a forward direction. We will prove, as usual, induction on number of edges. So our base case is minimum degree 3. Remember, we proved that minimum degree 3, which implies a break for a cycle extendable graph. And then we characterize the bricks. It will be either a wheel or a prism. And yes, it is belonging to our 4 infinite family, Z0 and G1 especially. It is generalized wheel and generalized prism. Now, next step is to induction step. So induction step is now minimum degree of G is 2. Let x0 is a vertex of degree 2 and we obtain graph G by bicontracting a vertex x0. What is bicontraction? Consider a vertex x0, which is a vertex of degree 2 and two neighbors x1 and x2. Contract both the adjacent edges of x0 into the one vertex. This operation called as a bicontracting a vertex of degree 2. And the reverse operation, where you consider a vertex of degree at least 4 and replace it with the path of length 2 and distribute all edges of x at least 2 at x1 and at least 2 at x2. This is called as a bisplitting, which is a reverse operation of bicontraction. One can easily observe that bicontracting vertex is a unique operation and the bisplitting is not a unique operation where we can split the edges at however we want. So yeah, so now we consider a J star obtained from G by contracting a vertex x0. We take underlying simple graph of J star. So J star can have a multiple edges. Now we take an underlying simple graph, which we called as a J. So we proved that J is also irreducible planar cycle extendable graph. And J have at least 2 less edges from G. So by induction hypothesis, we said J is also belong. We can say that J belong to our 4 infinite family or a kit. So now we have to get a graph G from J. So one we have to look that how J and J star are different. So how many parallel edges J star can have? So we proved that J star has at most 2 parallel edges. So that means we can get J as equal to J star. That means we didn't remove any parallel edge. We got J star as it is. Or we get a J by just removing a one edge from the J star. So from getting a G from J, we have to do a quasi bisplitting. What it means quasi bisplitting? Either we add one parallel edge to the graph J and do a bisplitter vertex, and we bisplit the vertex without adding a parallel edge. This is called as a quasi bisplitting. Now our main goal is to distinguish a good quasi bisplitting versus bad ones. What is a good quasi bisplitting? By doing a quasi bisplitting, we will get a cycle extendable graph that is called as a good quasi bisplitting. And once we got a not cycle extendable graph, which called as a bad quasi bisplitting. For all graph in Z0, Z1 and Z3. So now let's see an example of quasi bisplitting. So consider this graph. This graph is belonging to our family G1, generalized wheel, where color is indicating a half biwheel which we took. Let's add the parallel edge E. We got a graph J star. Now let's bisplit the vertex X. From getting a simple graph from J star, we have a unique bisplit to get a simple graph which is looking like this. Now the question is this bisplit is a good or a bad? That means is this graph is cycle extendable or not? Since I name slide as a good quasi bisplitting, it's indeed a good bisplit, and it's belonging to our one of the family, a double half biwheel family, where you can consider a one half biwheel as a blue, another half biwheel as a red. Both are C4, and we add 4 edges as I describe in the family. Now let's see another example. We consider the same graph G1 from G1 family, and now we'll bisplit vertex X. Now we can bisplit the vertex X for now getting a planar graph in the two way. One way is will look like this. The question is same. Is this graph is cycle extendable? That means is it good quasi bisplitting? And do we know this graph? We are looking this graph from the slide 1, which is H8, and this belonging to G0, G3 family. So this is a good quasi bisplit. And another bisplit we can do from here is look like this. And does this graph, now question is, does this graph is cycle extendable? If you look carefully, this graph is not cycle extendable. If you consider this cycle, if you delete the vertices of this cycle, you will get X0 as an isolated vertex. Now, since graph J is cycle extendable graph, and we did a bisplit at vertex X, and we got a non-cycle extendable graph. So how like what this creature is result, this graph is not cycle extendable. If you look same set of edges of this cycle which is not extendable in this graph, in the graph J, it will forms a good creature. That means it is a two cycle of same parity just share one vertex. And we have some special name of this kind of cycle called as osculating bicycles. So it is a cycles of a same parity which just share a one vertex x0. And if you do a bisplit in some particular manner such that neither neither of the cycle will cycle in the resultant graph, then union of the edges of q and q dash will give you a non-conformal cycle, such that if you delete the vertices of q union q dash, you will get x0 as an isolated vertex, which is our lemma, that let G be a graph and x0 is a vertex of degree 2. J star is obtained from graph G by contracting a vertex x0 if J star has an oscillating bicycle such that neither q nor q dash is a cycle in G, then q union q prime is a x0 isolating even cycle. And in all cases of quasi bisplitting, either we will get good quasi bisplitting will landed up in our family G0, G1, G2 and G3, and bad quasi bisplitting will give you oscillating bicycle in J star. So that's how we did a characterization of our main theorem. So to summarize, we saw some 4 equivalent definition of cycle extendable graph, and we prove one theorem, our main result, let G be a reducible planar matching graph. It is cycle extendable if and only if it's belonging to K2 and 4 infinite family. And I will show one last result of this and end of the talk. So this is a cycle extendable graph. I change the definition with the at least one perfect matching after removing the vertices of C. And let's see another class of graph called as a PM compact graph. The PM compact graph, that for graph G is called as a PM compact. So for each even cycle, after removing the vertices of C, has at most one perfect matching in the remaining graph. Equivalent to say that the symmetric difference of any two perfect matching is precisely one even cycle. And the original definition which PM compact is coming from, it says that a one skeleton of the perfect matching polytope is a complete graph. Now we saw a graph class where we'll get at least one perfect matching. We saw one graph class which we will get at most one perfect matching. Now the question is, what about the graph class where we will get exactly one perfect matching for each even cycle after removing the vertices of C? It turns out that is also very well-known graph class. It's called as a cycle force graph. A matching curve graph G is said to be cycle force if for each even cycle, the vertices of C, after removing the vertices of C, the remaining graph has precisely one perfect matching. And if you look this slide carefully, one can easily observe that cycle force is the intersection of cycle extendable and PM compact graph. And that is another thing. Interestingly, all 3 graph classes are well studied in the literature, but no one came up with this observation that cycle force is indeed intersection of cycle extendable and PM compact graph. And we can have a graph which are not cycle extendable and neither cycle extendable nor PM compact. This is one example, is a cube, which is not even cycle extendable or not PM compact also. And this is a summary of my results which we had done, which I came up with last couple of years. One is a planar cycle extendable graph, which we saw in this talk. I also characterize a bipartite planar cycle force graph and characterize some special cases of K2 3 graphs. One is a 3 connected, 3 regular and bicritical. And we have one conjecture that every K2 3 graph is either bipartite or a near break. One can observe that this result for a cycle extendable graph we got from the Carvalho and Little theorem. But for the K2 3 graph, we cannot use the result and say that every K2 3 graph is either bipartite or near break. So if we prove this conjecture for K2 3 graph also, then we can do the same, we can repeat the same procedure for the cycle extendable graph and get a K23 free graph characterization as well. But before that, we have to get the result for this conjecture. Yeah. This ends my talk. If you have any question, suggestion, comments, please.
Thank you, Aditya. So any questions from the audience? Looks like there are no questions. Thank you, Aditya. It was thank you for the nice talk.